Bienvenidos, Ushamdi, and welcome to Anne Arundel Community College. This is the first 8-week term of the spring 2019 semester, and this is the Networking 3, or the Scaling Networks version 6 course, CTS-230, section 845. In this activity, I'm going to be providing a tutorial and solution set for chapter skills number 2 on spanning tree. And so you'll remember from the diagram that we were dealing with a topology of 3 switches, and we needed to come up with a number of different data regarding which switch would be the root bridge, which ports would be designated ports, which ports are going to be the root ports, and then in this diagram specifically, which individual port is going to be the alternate or the blocking port. Now, that was kind of given away if you were to look at the image, because it was done in Packet Tracer and Spanning Tree had converged. So in the image, the alternate blocking port is actually highlighted as orange. So let's go ahead and dive in. I'm going to talk about the algorithm or the order of operations that you should use when you're trying to determine and lay out your environment. Now, some of you might be saying, hey, wait a second. Isn't this a copy of a video that you just did? And it is. So I'm actually teaching a course for instructors on CCNA security, and I had a student who is in the hybrid section of this course come in to get some extra hands-on time. And as we were talking about the topology, he said, I noticed that you said that the value of the links here is 2, and I thought it was 4. And that's when I realized that I had said that a 10 gigabit per second link has a spanning tree cost of 2. A 1 gigabit per second link has a spanning tree cost of 4. And you can see we're dealing with gigabit Ethernet interfaces here. Now, my mistake in take 1 of this video was that I thought, for whatever reason, I'll call it a senior moment, was that the cost was 2 for 1 gigabit, and that's how I did the video up. Now, the answers would be the same. However, I want to make sure that this is technically correct, and then we have 100 megabits per second, and that's the easy one because it's the oddball. It's 19. All right, so let's walk through this one more time with the correct spanning tree port cost values. So, the algorithm or the order of operations that you should be using, the very first thing you need to do is identify the root bridge. Remember, the root bridge is the center of the spanning tree universe. So how do we figure out which switch is going to be the root bridge? Well, we're going to be looking at the bridge ID. And the bridge ID is a value that actually is made up of 3 different components. And so when we talk about the 3 components that make up the root bridge, we're talking about the bridge priority value, which you see here. By default, that value is 32768. You then have the extended system ID, and so we'll say the bridge ID is made up of 3 components. And I'll just put PRI for priority. It's made up of the system, and I'll just put EI, the system extension ID, or extended system ID, I should say. So we'll say extended system ID, ESI. And it's made up of the MAC address. And together, these 3 values make up your bridge ID. Now, remember, in spanning tree, lower is always better, and there will never, ever, ever be a tie, which means that ultimately there will always be a winner for superior bridge ID. In other words, the lowest bridge ID. Now, in order to identify the root bridge, the very first value that we look at in the bridge ID is the priority value. Now, you'll notice on this activity that it was set to 32768. So if all of the priority values in the bridge IDs are equal, we go to MAC address. Now, a note on the extended system ID. This is a fancy way of saying VLAN. Now, for our activity and in class, we've been assuming that we're always dealing with VLAN 1, that we don't have multiple VLANs. If you had multiple VLANs, you would be doing the same exercise for each of those VLANs to determine where the root bridge is for that VLAN. Here, everything is VLAN 1. Excuse me. So, the first thing we look at is the priority value. Those are equal. Then we look at the MAC address. These are not going to be equal because MACs are, by definition, globally unique. Now, is there some hack that you could use out there? Possibly. Here, that is not the case. We are going to have a winner. So I always start at the first character. We see we've got a 0 here, and a 0 here, and a 0 here. That first hexadecimal character. The second character, 0, 0, 0. It's the third hexadecimal character that we're interested in right now. And we notice that switch 2 has D as in delta for the third character, whereas switch 1 and switch 0 have E as in echo for their third character. Well, that solves it. Here is my root bridge right there. Now, the algorithm, I'm going to continue to harp on this because if you follow this process, you're guaranteed to get the correct answer that you're looking for. So, number 1, identify the root bridge. In identifying the root bridge, first step, lowest priority. That would be the root bridge. If the values are equal, you go to the MAC address. The values will not be equal with the MAC address. There is going to be a decision made here as to whom the root bridge will be. In our case, it is switch number 2 is my root bridge. The next step is to immediately label all of the ports on the root bridge as designated ports. On the root bridge, all ports are designated ports. There are no root ports on the root bridge. So we've got designated port here and a designated port here. Now, the next step, we've identified the root bridge. We've labeled the ports as designated ports. So we have our designated ports. Now we need to find the root port on the non-root bridges. So how do we do that? Well, the number 1 criteria that we are going to look at first, just like when deciding the root bridge and evaluating the bridge IDs, the first value we check is the priority. On the non-root bridges, to pick the root port, we're looking for the lowest root path cost. And we'll talk about what happens when those values are the same. Here, that will not be the case. Root ports are going to be green. So I look at switch 0 and I say, if I go this way, and then I've got to come to switch 1 and then swing around through switch 1 going this way, my cost is going to be 4 for gigabit Ethernet. Make sure we get that right. And then 19 for fast Ethernet and 4 for gigabit Ethernet over here. So going to the left for switch 0, my cost is going to be 23. But I'm directly connected here with a cost of 4. So no question, gig 02 is my designated port. So now we come to switch 1. Remember, I'm sorry, didn't mean designated port, root port. It is my root port. So now we come to switch 1, where we're going to say which port towards the root bridge is the lowest root path cost. So I'm directly connected to the root bridge. However, the cost is 19 out of that port. And I put the value here. Remember, it's for the port, for the egress port, the outgoing port toward the root bridge. So the cost is 19 going this way. If I go this way, the cost is 4, and then the egress port here is 4. The cost is 8 as opposed to 19. So my root port on switch 1 is that guy. Now, we've determined who the root bridge is. We've labeled the root bridge's designated ports. We've gone to the non-root bridges and identified their root port based off the lowest root path cost. Now, we look at the remaining segments and we determine which ports will be the designated ports and which ports will be the alternate or blocking ports on those segments. So first things first, there's a little trick. On a segment where you have a root port, the opposite end of that root port is always, always, always a designated port. And it has to be. You can see here, root port, designated port, root port, designated port. It has to be a designated port on the other side of a root port because the root port is saying that is the shortest, i.e. lowest cost root path cost for me to get to the root bridge. So you have to be forwarding my traffic over here. So we can easily identify that that's a designated port, which brings us now to our final segment, which is this segment right here. So we already have a designated port here because the root bridge has a port on this segment. So we have to block the loop. So we know that this port must be the alternate blocking port, ALT. Boy, that was a terrible. Here, let me clean this up a little bit. This will be the alternate port, the ALT port. Alternate port, it's going to be blocking. And so what we did in class when we worked on our worksheet in the break area, and I'll do this in, let's do it in purple, is if you look at this, so where is traffic being forwarded? Well, it's being forwarded here, and I'll draw it in purple, and then it's being forwarded here. But are we sending traffic this way? We're not, because this port is blocked. So look at how Spanning Tree sees the layer 2 topology right now. Spanning Tree sees the layer 2 topology with these two active links. So there is no loop because we are blocking that port right there. So which questions did we have here? It says determine the root bridge, lowest bridge ID. We did that. Label the bridge ID of all switches. That information was provided to us. Then, once you get the root bridge, the first thing you need to do is label the designated ports on the root bridge, and that will be all ports on that root bridge. Then you're going to label the root ports on non-root bridges based off the lowest root path cost. In other words, the shortest path will be the cheapest, lowest cost path that you're going to take. And then we did that. If it's a tie, it's going to be the lowest sender's bridge ID. And our next diagram is going to give us an opportunity to take a look at that. Then you're going to label the designated ports, which would be on the opposite side of the root ports. And once you do that, for any segments where there's not a root port, and you could have a designated port, or there could be no ports identified yet, you're going to determine which port on the switches is going to be the designated port and which is going to be the blocking or alternate port. So the first thing that you do is who has the lowest cost of the root bridge. And again, if we're looking at this segment down here, this bottom segment, well, it's obvious. The cost of switch 2 is 0. It is the root bridge. So the BPDU that switch 2 sends out onto the fast Ethernet segment and the BPDU that switch 1 sends out on the fast Ethernet segment clearly show that the root path cost for switch 2 is the best. Therefore, it would have been the designated port anyway. We know that because it's the root bridge, but had it not been the root bridge, it's got a superior, i.e. lower root path cost. It becomes the designated port for that segment. And then the opposite side has to be blocking. It's an alternate blocking port. All right. So we've got our topology. There are your answers for everything. I think it asked you what the root bridge was. We've got that switch 2. Switch 0, gig 01 and 02. 01 is your designated port. 02 is your root port. On switch 1, fast Ethernet 01 is blocking alternate, 02 is the root port. On switch 2, they're all designated ports. And again, recovering from my senior moment in the first video, the cost for gigabit Ethernet is 4. It is 10 gig. That is 2. So there's the solution for the first topology. Now let's move on to the more challenging second topology. So let me go ahead and clear the screen here, and we're going to scroll up just a skosh. And there it is. That is the second topology that we're going to be dealing with. When we look at this topology, we can see that clearly this is going to be a little more difficult to sort out than the first topology. So what I'm going to do is in black, or actually, let's see what, not a lot of colors to choose from here. Yellow's not going to show up. I'm probably going to use green. I'll use brown. So gigabit Ethernet, cost is 4. Fast Ethernet, cost is 19. I'll put the cost in brown for all of these links. So all of these links here, the cost is 4. Cost over here is 19. The cost here is 4. So that is the spanning tree port cost for all of the links that we have in front of us. All the gig links are 4, and you can tell I'm stressing this as trying to recover from the mistake I made. So the gigabit Ethernet cost is going to be 4. The fast Ethernet cost is going to be 19. So we'll go red, right? Remember the root bridge. The root bridge is the center of the spanning tree universe. So what is our algorithm? Number 1, we identify the root bridge immediately. How do we do that? We check the bridge ID values. We first look at the priority. If the priority has been changed, lower is always better. There will never be a tie. So we look at the priority values here. They're all the same. So for the bridge ID, the next value that gets examined is the MAC address. So here we have 0001, 000A, 0006, and then 0030. Here is my root bridge because 0001 is lower than 0030. It's lower than 0006, and it's definitely lower than 000A. Remember, A in hex is equivalent to 10 in decimal, right? So there's my root bridge. So the algorithm, identify the root bridge. First step, look at the priority values. Second step, if they're all equal, look at the MAC address. Once you identify the root bridge, we label our designated ports. All ports on the root bridge are designated ports. They are all forwarding. They have to be. It's the root bridge. Next step in the algorithm, identify the root port on the non-root bridges, and we'll switch to green for this. So we'll just go in order. So switch B. Going out that port, my cost is 4. Coming out this port here, it would be 4, and then 19 is 23. Coming this way, it would be 19 and 4 is 23, or 19 and 4 is 23, and 19 is 42. Yeah, 42. So no doubt, my directly connected link right here with a cost of 4, this is going to be my root port. Now, remember, we don't start diving into the other ports on that switch. We identify for each individual switch its root port, each non-root bridge. We find the root port. So we got switch A is done, switch B is done for root port, switch C. So switch C is directly connected, and this is what's not really intuitive here, is you would look at this and think, well, it's directly connected. That has to be the root port, but it's not, because Spanning Tree doesn't care that it's directly connected. Spanning Tree cares that the root path cost to reach the root bridge out fast Ethernet 01 is 19. So let's take a look at the other options. We could go out that port right there, up to switch B for a cost of 4, and then this way for a cost of 4. So that cost would have been 8. And so going that way, it would be 19. Now we've got this link here. I could come to switch D for a cost of 4, and then out switch D's interface here, and the cost would be 8. And we already know that we're not going to come out that interface because it would be 4 and 19. And switch D is going to be sending its route path cost, its best route path cost, which is going to be going this direction here across that link for a cost of 4. So when we look at this, we say, well, it's a cost of 8 to go this way, and it's also 8 to go that way. So here's where we run into the tie, or I shouldn't say the tie, where we have a tie in the values, or we have the same value. But remember, lower is always better. There is never going to be a tie. So when the values are the same, what is the determining factor? Exactly. It's going to be the sender's bridge ID, the superior, i.e. lower, better bridge ID coming from the switch that is saying, hey, if you go this way, we'll get there with a cost of 8. And the same thing, hey, if you come this way, you're going to get there with a cost of 8. So who is telling switch C that this is their best way to get there, and switch D is telling switch C this is my best way to get there? So the sender's bridge ID is going to be switch B sending its bridge ID down to switch C, and D is going to be sending its bridge ID over to switch C. And so switch C sees that the cost will be the same, therefore I'm picking the path who has the sender with the best bridge ID. So when we look at these two switches here, B and D, who has the lower bridge ID? It's D. 0006 is lower than 0030. So here is the root port on switch C. It's going to be gig 11. That leaves us one switch to go, switch D. We know that it's not going to be going that way. The cost would be 23. And we know it's not going to be going this way because the cost is, again, 23, because it's got to come out that interface at a cost of 4 and out this interface at a cost of 19. Here it's a cost of 19, and then it would be a cost of 4. So it's going to go that way. It's a directly connected link in this case, and the cost will be 4. Gig 12 is my root port. And so now let's go ahead. We'll change back to red. And this is kind of a little, I like to call a wrinkle in the order of operations. So again, number 1, identify the root bridge, the center of the spanning tree universe. You do that by finding the root bridge with the lowest priority value. When the priority values are the same, you go immediately to the MAC address. You're not going to have a tie with the MAC address. Find the root bridge. Label the root bridge's ports all designated ports. Once that is done, you go to the non-root bridges and identify their root ports. You do that by determining the lowest root path cost, or the shortest path, the lowest cost path to reach the root bridge based off the spanning tree port costs. On switch B, that was pretty easy. It's the directly connected link at a cost of 4. There's my root port. On switch D, same thing, directly connected port with a cost of 4. Lowest root path cost, that's my root port. On switch C, we figured out and calculated the cost, but we had the same values for 2 different paths. When there is a tie like that and the values are the same, there's not going to be a tie. We're going to go to the superior sender's bridge ID, or the SBID. And we know that the sender's bridge ID, that is the superior value, the lower value, is coming off of switch D. That would be switch C's root port right here. So now, if it's not already done, you would look across from every root port and ensure that we have a designated port. So on switch B's root port, yeah, designated. D's root port, other side, designated. C, that gives away that that is going to be the designated port. It has to be the designated port on the opposite side of the root port, because the root port is the port out which all traffic is flowing. So you can't have that port blocking. That makes no sense, right? So it's got to be a designated port. So now we're down to 1, 2, and I think 3 segments. We've got 3 segments we have to work out. And we have to determine on these remaining segments which port will be the designated port, and on the opposite side, which port will be the alternate blocking port. So let me go ahead and change my color to blue for the blocking port. So this is the root bridge. It's got the superior root path cost. Obviously, it is the root bridge, cost of 0. So the other side over here, here is my alternate blocking port. Fast Ethernet 01 on switch C. Now let's deal with this segment here. Remember, we're talking about just that segment between these 2 switches. So switch C's root path cost is what? It's 8. Switch C has to come over to D and then go up to A. Switch B is directly connected and has a cost of 4. So, very easy. That is the lowest root path cost. There is your winner as the, oops, sorry, let me do it. Keep the colors the same here. That will be the blocking alternate port on this side. And the designated port will be this one right here, because switch B sends a BPDU out on that segment. C sends its BPDUs out. They compare the root path cost. Switch B is your winner. So designated port to switch B, alternate port to switch C. That gives us our final segment over here on the far right, which is the fast Ethernet segment between switch B and switch D. So switch D has a root path cost of 4, the single individual gig interface. Switch B has a root path cost of 4, the single gigabit Ethernet interface. So we have equal values there. Remember, lower is always better. There will never be a tie. So what happens now is the BPDU gets sent from switch, and they're sending these BPDUs every 2 seconds. So I'm just kind of walking through, okay, the BPDUs are being sent, and what value are we looking at? We're looking at the sender's bridge ID. So the bridge ID of switch B comes onto the segment, and he says, hey, my priority is 32.768, and my MAC is 0030. Switch D says, hey, my priority is 32.768. Excuse me, my MAC address is lower than your MAC address. Lower is always better. There will never be a tie. So switch D says, thank you very much. I am going to go ahead and I am the designated port because my bridge ID is superior, i.e. lower than your bridge ID. And so what does that leave us with? We'll come down here, and that is my alternate blocking port. Now, let me do this where I go to purple or violet, and we've got an active path here, and I'm basically highlighting the spanning tree, the active forwarding spanning tree path. We have an active path here, and we have an active path here. So what do we have? Are there any loops here? No. The active layer 2 topology here is flowing this direction. Now, you may be asking yourself, okay, this is great, and I didn't talk about this in the first video where I completely wiped myself out with the cost. The answers are correct, but I was using 2 instead of 4. So I didn't talk about this, and I want to give you some real world applicability here to what you're looking at right here. Let's say that this is how your environment is cabled up. And let's say that hanging off of switch C, you have PCA. Now, in the first video, I talked about when you go into an environment, it's very easy to tell if the network engineers gave any prior planning and forethought to how they were going to lay out their topology. And this is something that I run into often in a lot of environments, is that all of the priorities are the default value, and the engineers just simply willy-nilly in an ad hoc fashion plug cables in just like you see here so that they'd have lots of connections between the different switches, thinking that, oh, well, I've got all these available paths and all this available bandwidth. Well, again, look at this purple line that we've got going on here. This is the active flow of traffic in this environment. That is how traffic is going to flow from PCA here. If it's hanging off of switch C, what if your router is over here on switch B? And that gives you your connection out to Verizon or Comcast, the internet cloud. So the network engineer might have thought, well, I have this gigabit Ethernet connection that goes directly over to switch B. But if they don't take this into consideration, look at what just happened. PCA's traffic is going to have to go from switch C over to switch D. Then it's going to have to go from switch D, because this port here is blocking, so it's not going to sneak out that segment there. It's got to come all the way up to switch A. And then when it gets to switch A, then it comes over to switch B, and then it's going to make its way out to its default gateway, router 1. And this is what can happen if you don't understand how spanning tree impacts the forwarding of your traffic at layer 2. So you might be asking yourself, okay, Travis, well, that's great. You know, this is this contrived setup here where we've got fast Ethernet links, and this is, you know, maybe you wouldn't have this, maybe you do. So what can I do to fix this? And we talked about this. If I were to draw a line right through the middle of the topology here, right? And if we were to say that this is our access layer down here at the bottom, and that this is our core/distro layer, it could be collapse core, it could be just the distro, right? But this is the recommendation, is that as a best practice, you want predictability in your environment. You want to know what's going to happen when something fails. So you would always, 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 always determine manually the root bridge. And we're going to set the priority to 0. You would always set the secondary root bridge, or the root bridge that's going to become the root bridge if the root bridge fails, the secondary root bridge, to 4096. And then at the access layer, you would set them to 61440, because you do not want a switch that's down at the access layer becoming your root bridge. And again, this then begs the question, well, you know, because think about it, this link right here that goes from switch C to switch B, do we even need that link? I mean, right now in this topology that we have configured, that link is useless, right? So that's not even being used. So that's why we want to make sure that we plan things out so that there's an opportunity for the best links or the best paths to be selected. And this is a great segue into what we talked about Thursday night, which was Ether Channel, which is bundling multiple physical links together. And you're getting the additional bandwidth, not throughput. Remember, the additional bandwidth becomes available, right? So in an enterprise environment, you're going to set your root bridge to be one of your distro switches. You're going to set your secondary root bridge to be the other. You're going to manually configure those values like that. And then you're going to set these manually to the highest possible cost, meaning that you would have to lose both distro switches before one of these is going to end up being the root bridge. And if you've lost both of those, you have bigger issues than the root bridge being at the access layer. And so hopefully this has sort of demonstrated the unintended consequence of just plugging all your switches in, not really truly understanding how the layer 2 traffic is flowing. And if your router's hanging off switch B, you may think, oh yeah, this is going to work great. My traffic's all going to go that way. No, it's not. It's going to come this way, right? Like the backwards Z. Okay, so the questions we had. Root bridge. We know the root bridge is switch A. The port roles. All of switch A's ports are designated ports. Switch B. Gig 1.1's your root port. 1.2 designated. Fast Ethernet 0.1 blocking. Switch C. Fast Ethernet 0.1 blocking. Gig 1.2 blocking. Gig 1.1. I think that's a 1 underneath there. Gig 1.1 is your root port. Switch D, Gig 1.1 designated port. Remember, it's opposite of a root port. Gig 1.2, I'm sorry, yeah, designated port, Gig 1.1 on switch D, Gig 1.2 on switch D. Fast Ethernet 0.1 is a designated port. And the opposite side of it just happened to be a blocking port. And then the last thing they asked you, Spanning Tree Protocol STP was originally, or is IEEE 802.1D. RSTP is 802.1 lowercase w, and VLANs 802.1Q is how those were originally defined. All right. Well, that is going to wrap up this video tutorial, take 2, making sure we're using the right value for the gigabit Ethernet cost of 4. Thanks so much for watching. I will see you all on Thursday night. And again, I left all that up there. There we go. I will see you guys all again on Thursday night. Have a good one.